So thanks for having me. It looks like a very exciting summer school. I enjoyed the talk that I saw, only one talk yesterday, but I thought actually before we get started to make you actually work. So as you see, or as Carsten told you, and it's actually all correct, so I work with specialized hardware in an effort to make databases or data-intensive systems more efficient. These days, I'm also looking at other aspects, and I'll come back to that at the very end of the talk. But what I would like to hear from you, and maybe not so much from the speakers, but from the students, just say your name, because I don't think I met every one of you yesterday evening. And just in 3 words, like the way I did, describe what you're working on. And maybe it's also useful for me to know where you are in your career, because I guess people are in a different point. So that, it's nice to meet you this way, and it also helps me calibrate the talk. So I guess we'll, just please start from wherever this also wakes you up, I guess. Okay. So thank you everyone for, I think this was, at least for me, very insightful. It's quite a colorful crowd. And I think, or I hope that the talk will be useful for all of you, even if you're not, in the business of designing specialized hardware or accelerators. Hopefully this gives you a perspective of, what are kind of some of the caveats, or what are the challenges that we face, and even beyond that, at the meta level, like when should we try to do specialization? When should we try to incorporate other types of hardware in database systems? So the context for the talk will be databases with large data sets, kind of looking at OLAP. And since from what I hear from the room, I don't really need to explain what OLAP is. So just assume that we're doing, your typical OLAP workloads. And just as a reminder, I'm thinking here of query plans with more than one operator, where you can move things up and down. So basically, you have some flexibility in how you run your operations in your database. And as a motivation of why are we talking about acceleration, using FPGA acceleration of analytical databases? Well, of course, there's a lot of money involved in databases. And I guess this number is now getting more and more outdated, but since 2018, there's only been a further increase of data sizes and a further increase of analytical operation or interest in analytical operations. So the premise still holds. Databases are a huge market, and we want to make them more efficient. The question that we're going to look at for the next half hour or 40 minutes is whether we could specialize machines to them. And the idea here is that through specialization, we can basically make them even faster or more efficient, or get some other properties that otherwise you wouldn't have. And through this, basically, gain something. So we'll start with time travel. And we'll go back in time to the 70s. And this is a time where many of us were not even around. It was a different time, free love and Woodstock and what have you, but people have already been working very hard on database research. And there was this project from Ohio State and IBM Research and I guess other collaborators on designing a database computer. And if you read, I kind of took verbatim from the paper, their motivation is to handle a very large online database of 10 to the 10th bytes. So this, today maybe in the terabyte age sounds like, okay, we're talking basically here about, tens of gigabytes. But for the time, this was, I think, something groundbreaking, right? This is basically talking about like petascale computing today. And what this project actually built is a truly specialized database engine or database machine that is shown here on the right. You don't really need to understand everything, but what is interesting is all these blocks are kind of specialized processors or specialized elements. And they use really, the greatest technology they had available at that time, which was special instruction set microprocessors. And for memory, they use, the cutting edge thing, magnetic bubbles and charge coupled devices. This is something where you probably haven't even heard of these technologies. Has anybody heard of magnetic bubble based memory? Okay, so
the bubble memory.
okay. So, but then if you heard of it yesterday, I will not spend time.
Not in detail.
So the idea back at this point, like when random access memory was not really a thing yet, the way that people used to store data is to rely on basically delays in various physical phenomenon, like a capacitor or a charge, basically going through some medium. And then your memory would be, logically, you can think of it as a tape, which goes around very slowly. And then like a carousel that brings the bits to you. And then basically you can like store things there, but you will have to wait for it to come around so that you can read the bit if you're interested. So this was a very, very interesting project, but it basically became unfeasible, or it died because semiconductor technology advanced very rapidly in the end of the 70s, and general purpose CPUs took over. So, okay, this was one try. In the 80s, again, different vibe, neon lights everywhere, disco, I guess, 80s. There was another idea, the gamma machine. And this time, this is University of Wisconsin. And here, what they built is actually surprisingly similar, I would say, to how we think about databases today. It was actually groundbreaking. It was a VEX, so that's a kind of an older CPU technology, VEX-based multiprocessor system. If you look here at their design, they basically had different processes doing different things, kind of looks like a distributed system. Actually, the storage devices could perform some operations. So whenever some old grumpy guy stands up at a conference and says, what is new with your research? We've done this in the 80s. Sometimes it's good to listen because actually they might have done something like that in the 80s. It doesn't mean they've done the exact same thing, but it's interesting how much of these ideas like near data processing actually have been around in one shape or form. So what happened to this project? Why, you might ask, why do I not know about this, or why is Gamma Machine not the success product up to today? Is because they were developing it at a time where Moore's law was basically well and alive. And by the time you developed the hardware needed for the system, general purpose CPUs basically just leapfrogged the system in performance. So what the authors did here, they spent many years working on the system. But of course, when you start working on the system, make the design, you kind of cast some design decisions in stone, and it will take you years to actually make it happen. And in the same time, general purpose CPUs just got much faster. So if we look at kind of history, or look back and try to understand why is that the specialization kind of failed and again and again in the past, it has to do with the way that general purpose CPUs performance was increasing. So what you see in this graph is a timeline from the early 90s up to present day. And what I'm showing is here the number of logical cores on the x-axis, or on the black point, and frequency of CPUs, which is a proxy for their performance, with the blue. And this is a log scale, so actually there's like an explosive growth of computing performance. So maybe one question: can somebody in a very simple term explain what Moore's law stipulates? Which is actually not the law; it's more like an observation of what happens in practice. But can somebody summarize it for us? Yeah.
Every 1.5 years, amount of transistors in one chip increase double.
Okay. Yeah. So to even simplify over some time, so maybe 1.5 years, you get some multiplier 2 times the number of chips, the number of transistors that you can put in a chip. So this is good, but if we think about it just with Moore's law, it doesn't really explain why where CPU is actually getting faster. I mean, you get more transistors, but I mean, how is that beneficial? So the other part, which was in the equation, is the Dennard scaling. So can somebody explain what Dennard? Do you know what Dennard scaling is? Again, in layman terms. So let me kind of explain. The idea here is that we said with Moore's law, we basically have some number of transistors, and then every 2 years, we basically can build a chip which has now double the number of these transistors. At the same time, there's shrinking in process technology. So basically, you can make these transistors smaller. And what this actually results is that these 2 times of transistors, they fit in the same area that the original, like the previous generation chip was in. And what linear scaling does, or what, what's the effect, is that by having smaller transistors, you're basically operating more efficiently, which allows you to decrease the voltage, increase the frequency. So in layman terms, it basically allows you to run more transistors at the same power as before at a higher frequency. So what this meant is you were getting more transistors, they were running faster than the previous generation, and you didn't have to pay more power budget for it. So if you could fit in 100 watts, then in 2 years, you got twice the amount of transistors, still the whole chip taking 100 watts, and potentially even running at a higher clock rate. So this was amazing. This was like, as I said, this was free lunch. If I had an idea here for a specialized system and I worked very hard for 5 years, and the specialized system would give me a 2x speed up, if I would do nothing for 5 years, just sit back and drink beer, it would be very bad for my health. But I could just basically buy a CPU in 5 years that has, almost 10 times the performance of the one that when I would have started with my project. So things have changed, however, and around 2006, linear scaling basically stopped applying. So if you want, I can maybe discuss this after the talk, but by shrinking the transistors to some size, you start seeing other type of effects, and power behaves differently, and the difference between static and dynamic leakage in the transistors shifts in their importance. Long story short, from this point on, you couldn't actually increase the frequency of the chip without increasing also the power consumption. So the answer was to start looking at basically multi-core processors and try to keep performance high that way. But as we all know, using a large number of parallel cores on a CPU is not a trivial task. Amdahl's law is constantly hurting you there, because even just a little portion of the application which is not parallelizable will keep you bounded in how fast you can become. So around the 2010s, we started seeing a problem where CPUs are basically, we can say in a simplified way, are not getting faster. At the same time, data has been exploding. And of course, I guess you can draw this line any way you want, but there's an exponential explosion of data sizes and problem sizes that you want to solve. So what this means for specialization, and maybe this is one of the takeaways of the talk that I want you to remember, if nothing else, is that if we look at introducing specialized hardware or heterogeneous hardware or new ideas, new hardware ideas to databases, up to the early 2000s, there was basically an incentive not to do it, because if you would just wait, the CPU scaling would give you more benefit than building your own multi-million-dollar project, and you will get an older technology out than what CPUs would give you at the time it comes out. Then in the 2000s, logically it made sense, but economically it didn't, because everybody was moving to the clouds. And if you remember, the beginning of the clouds was a highly commodity-based business. So the first cloud, the idea was that you buy the cheapest hardware off the shelf, standard things, not the big label brands, but you buy the cheapest hardware, put it in a big data center, and operate it as cheaply as possible. And this way, basically, be more efficient than traditional data centers. However, and as I heard, from your work, many of you are already interfacing with AI, machine learning. As these workloads came in the cloud, it became clear that CPUs were not fast enough for them. So I think that was actually a very interesting shift. The moment GPUs became a standard element in the clouds, it basically opened the gates for other kinds of specialized hardware, right? Other kinds of accelerator. The moment you accept it's not only x86 processors, but you can have other things in the cloud, basically you are in a new era, which I like to call the specialized hardware revival. So now, basically, there's from the CPU side, there's an incentive to do this because we will not get faster CPUs. And also economically, it makes sense because if we deploy this in the clouds, they are used to specialized hardware. there's a lot of different workloads that are running, and you can actually make this happen. Right. So to give you an idea, I guess many of you in the room have already some knowledge of FPGAs, but I just want to kind of give this idea of why is it that we say that specialized hardware, or how do they help with efficiency, or how do they help with overcoming the challenges of CPUs? Well, if you think about it, so kind of coming down to energy efficiency of how many operations I can do per unit of power, normal CPUs are not very efficient because you actually spend, depending on how you count it, but by some, let's say, accepted estimates, somewhere around 70 to 90% of arithmetic operations you actually spend on bringing data to the registers, on decoding instructions, managing the instruction cache, and so on. So basically, here, it's not that CPUs are designed by people who don't know what they're doing. It's just simply the fact that they're general purpose flexible processors introduces overhead in the system. And then as you go to the right, because you're specializing more and more to your application or use case, you basically get more efficiency. So the FPGAs that I guess will not really talk about the details, but I'm again happy after the talk to chat with those of you who are not very familiar with FPGAs to explain how they actually work. And maybe just to kind of tease you, I will say maybe FPGAs are the real computing in memory, but I'll explain that to those who don't understand this statement in the coffee break. So what the FPGAs are is basically a big sea of programmable elements, a chip which can be configured to the operations that you want to execute with a free choice of architecture. So there's no instruction set. It really just does the operations that you want. And you can play with ideas of fine-grained pipelining. You can tailor your communication between modules. You can use distributed scratchpad memory to use things. So the difference between a multi-core processor, just again to give you an idea, and something like this, because this is also parallelism, right? In the end, this is also kind of a parallel chip where you can do things in parallel. The difference is in flexibility, that you can choose how you implement your data flow parallelism. You can tailor your communication across parts of the chip. But there's one trade-off in that all code occupies chip space. And this is, you can think of it as if I build a database filtering operation with 3 different steps, they will take up some physical area on the chip. And this is the same for FPGAs or ASICs. I mean, basically the circuits that you use for processing will take up physical space. I think what is interesting with FPGAs is that they themselves are an evolving platform. Due to the highly regular architecture, actually, they still kind of benefited from Moore's law improvements, but that will not hold on forever. But for now, actually, these devices have become quite, let's say, powerful and capable. Right. So maybe as a, let me just go. Maybe as an overview of how we deploy these accelerators, and this is something that I think is important for databases, is the choice of how you look at the accelerator, either physically or logically, will also have an effect on how you can use them. And I typically like to categorize these accelerators into 3 categories. So one is on the side, which is GPUs, for instance, where the data is owned and managed by the CPU and is sent to the accelerator for processing. And this actually works very well if you need to do relatively lot of processing and relatively little data movement. There's the other type of acceleration, which is in data path, which is some of you mentioned, things like near data processing or in-network processing. Is basically what they refer to is this kind of model where data is going from somewhere to the CPU or from the CPU to somewhere else, and then you try to do something clever with it when it's moving. And then we also have the coprocessor model, which is basically saying, instead of adding something on the side, I change the way the CPU operates and I add in additional capabilities. So one example of an accelerator in the CPU that you maybe don't think of like it is all the basically the SIMD instructions that you're doing, you can think of them as an accelerator. So AVX is a mini accelerator sitting inside your CPU. So as you are probably all familiar with the systems, and I'm here, I kind of picked the FPGA-based accelerators. They are present in the cloud. So you can do on-the-side acceleration with things like Amazon F1. In the data path, I think the Microsoft Catapult project and the Amazon Aqua are the most representative. And then actually this one is a project that doesn't exist anymore. It was a co-processor kind of setup with CPUs and FPGAs. But I think it's coming back in a smaller form factor. So for the server grade CPUs, perhaps it's not happening, but you see a lot of things in the SoC space. So I think for the edge, actually the co-processor model will hold. Okay, so I kind of took long in the introduction, but that's not a problem because in the end, my message is not too complicated. I would prefer that all of the things I explained so far are clear and will stick with you rather than to go into very gritty details. So I'll just kind of show you in the next few slides why, when people think of hardware acceleration, so even in this hardware, revival era, a lot of projects that propose hardware acceleration for databases fail. In the end, they don't really get an impact. And let me give you some reasons of why that happens. So one issue is that people often look at FPGAs or other accelerators and say, I have an idea for making an operation go faster, and we'll deploy it as an on-the-side accelerator. The ugly truth here is that even if you reduce your compute by, for instance, 2x or 5x, you're introducing other overheads that didn't exist before. So like data movement basically becomes an additional cost. And this ends up in the end, not really offering a real speed up. So this is, I think you all read these papers where the idea or this accelerator looks amazing. But in the end, if you really look at the query from beginning to end, it doesn't quite add up. So that's a bummer. The second thing, which often happens when it comes to hardware, and again, I'm looking at it from the perspective of FPGAs, but this happens also with GPUs, is maybe you have some kind of clever idea to build a data structure and operation that works very efficiently on this accelerator. So maybe it's a fixed capacity hash table on an FPGA, and it's something very clever because you can use the distributed memory on the FPGA to do very quick lookups and do some transformations. And this is all good, but because it gives you constant access or much higher access rate than what you could get on a normal CPU. But it has a problem because what happens if you don't fit all the data on the FPGA? So maybe sometimes you don't know what the problem size will be, and you start computing, and then you realize halfway through that it doesn't fit. The same applies for some GPU research, where I think again it's very common that things work well as long as data sizes or active data sets fit in one or other part of the memory or exhibit some level of parallelism. But if that doesn't happen, then things fall off a cliff. And this is something that again has been basically taking away the benefits of these clever ideas, because if you're now in a database where option A is that everything works amazingly well, and option B is that the world explodes, you will not like it very much. The query optimizer will not like it, that these are the two options. So then you would prefer to say, let's not use this specialized hardware and let's stick to the CPUs and let's stick to the resources we already know. And then the third fact, and this is not so much, this is what it is. Basically, analytical databases have become more optimized. Or you can say there's not so much compute in core SQL. So of course, when we talk about OLAP, I think this is an overloaded term, and some people think of big data system, machine learning pipelines, OLAP, but there's also OLAP, which is like running the accounting forecast and the market performance analysis of a medium company. And if we think of the previous one, we know already from the time of X100 that basically if we use row stores, then most of the time we spend on things which are not actually related to computation. So this is again just to highlight that what happens is, of course, we know. So if we do a column store layout, then we're basically often removing these overheads, and we're actually able to run at the speed of the memory, so at the memory wall. And again, this is a sin, I would say, even more than the previous two. What a lot of specialized hardware research does is they take as a baseline a row-based database or row store, or a database which is not optimized for the operation that they are, pretending to accelerate, and then they get a great result. But if you actually would compare your accelerated database to a state-of-the-art column store, you might actually be on the losing side. Okay, so maybe we shouldn't be looking at hardware acceleration for databases. Well, let me kind of turn it around to the positive and give you some ideas very shortly of how each of these actually can be turned into an opportunity. So I think for me, what I feel is actually one of the most exciting aspects of modern database systems is this whole notion of disaggregation, this whole notion of thinking of the database as a distributed system. So even if it's in a single machine, I think already there's a lot of kind of logical decoupling of elements and data flow kind of parallelism. And, databases have changed from this big monolithic beast to something which looks to me more like, a playground of blocks that send data to each other. And maybe one way to look at the hardware, the use of specialized hardware, is to reduce data movement bottlenecks. So instead of saying I accelerate an operation, let's think of reducing data movement bottlenecks, because in the end, as you saw yesterday, it often what limits us today is how quick we can move data around. So I'll just put this up without too much explanation. But we looked at the beginning of my PhD, for instance, this idea of processing inside an SSD and using an FPGA to filter out operations that go to the CPU. Not because the FPGA would have been faster than the CPU at doing these operations, but because this link between the SSD and the CPU was the bottleneck. And doing it in the FPGA would allow you to actually be faster. In the meantime, this has become kind of a standard idea. You have the Samsung Smart SSD, which is a real product and you can buy, has FPGAs inside. There's the Amazon Aqua. Redshift is basically by default accelerated with a similar idea. And the similar idea is basically the other project I was working on in my PhD, which is moving this to the distributed systems space. So looking at storage not as an SSD attached to a machine, but storage as network storage. But again, the story is the same. The bottleneck is often this link between the distributed storage and the processing nodes. Okay, I'll just skip this. But basically what is interesting in this setting is that when we start looking at, or if you look at filtering pushdown, so processing in storage, of course you could implement that with traditional CPUs. And if you implement it with traditional CPUs, so basically say now my storage node does some pre-filtering operations. There is a challenge which is guaranteeing that filtering never slows down retrieval. So it could happen that here on the right I'm showing like a key value store that you're doing some pre-processing on each key. And what you just really need to see here is that as you add more and more operations, your relative throughput might go down because the CPU in the storage node will become compute bound. Where specialized hardware brings something interesting is that you can actually express the processing in a different way. You can make it data flow, you can make it bandwidth bound instead of compute bound, and get the behavior where basically, regardless of what operation you're performing in the storage, you will get the same throughput. And maybe this has to be said, it's not that you can do arbitrary operation, but operations which have been provisioned, or in the space of operations that you're able to do, you can basically pick any combination and it will work well. And this is important because when we think of this question of predictable behavior or query planning, this is making your life much easier because you know what you will get every time. And this kind of brings us to the second topic, which is the all or nothing behavior. And I think this is where we need to think of hybrid processing, basically thinking of ways in which we split or share computation across specialized element and CPU in a way that allows a smooth transition across the two. So in this example of IBEX, for instance, we have introduced also group by aggregation that pre-aggregates tuples on the FPGA. And for this, as you remember, or I mentioned the hash table, so we use basically a hash table on the FPGA. And this is all, so this would be like if you wouldn't do the aggregation on FPGA, so you would then take the input table, do projection, selection, and then send the tuples to the CPU for group by. But you could further optimize this by doing the group by on the FPGA. But as I mentioned in an earlier slide, the problem is that now if this group by cannot actually compute the final solution, I'm out of luck, because maybe then what I have to do is basically cancel the query, throw out everything I've done, and restart with the group by being on the CPU side. So now, when you look at it, the solution might look very simple, but basically what you want to do is to perform kind of a partial aggregation here and then finish it up on the CPU. In the end, the idea is really that simple. So just saying, whenever you look at hardware acceleration, think in ways in which you can basically do this in a hybrid, in a graceful manner. Not that everything is, you don't put all your eggs in one basket, but basically you split computation across these devices. And group by was actually a very nice example, because if you think of something like count, the amazing thing is I can basically run a group by instance on the CPU on the same schema, on the same tuples, and just perform, if I send partial groups from the FPGA, I can just basically sum them up, and then I have the count on the CPU side. I don't need to implement a new type of operator. That's what I meant. You just use standard SQL ones. And what we saw in the paper, so just to explain, this is here execution time, so lower is better. This shows how much of the tuples have to be post-processed on the CPU side. And then here, so this is a little bit older paper, so my ISAM, I think you don't really see it so much these days, but this is one of the storage engines that MySQL supported at the time. And you see that if you run everything in CPU, well, I mean, it basically doesn't matter how many groups there are or how large the groups are. But then with our kind of hybrid solution, you can basically go, if everything fits on the FPGA, then we get a very good performance, and then it will degrade kind of slowly to the same performance as you would get on a normal CPU. Actually, we even had like a custom implementation where, by knowing now that the FPGA will always pre-process groups, we could optimize, for instance, the CPU side of group by, and we didn't have to think of what happens if I have 1 million groups or something like this, because we knew that the data set will be smaller than if you read the data directly, so we could actually optimize for more like in-cache processing and stuff like this. But this is kind of one of those nice benefits where if you start thinking of a hybrid system and all the elements together, you might be able to optimize each part even more. Okay, so this is almost it. So we solved 2 of our headaches and kind of looked at new challenges that open up. And in terms of analytical databases, becoming more optimized and not much compute in SQL, the good news is that, and as we all know, there's a lot more compute problems coming our way. So if we look at, how now, I guess machine learning is a household name. It's everywhere. Databases, have them. People want to do it. It's basically an invitation to start looking again at these compute-intensive operations. And specialized hardware can be useful there. I skipped this just in the interest of time, because I want to still get to some points. Is it what happened? Okay, so I think, looking forward, we should be optimistic. There's, let's say, there's a lot of challenges, but like good challenges ahead of us. And I think specialized hardware can bring answers in all of these. There's a few open questions, like understanding or figuring out ways in which we can derive accelerators from user queries. This is, I think, something where, a lot of the work that you've probably seen or you yourself have done is often a domain expert like yourself is sitting there looking at the problem, thinking very hard, and then proposing a solution. Of course, in the long run, what we would like to have is a more automated way of deriving these accelerators, be it FPGAs, be it GPUs. I think even for GPUs, one could claim that we don't have a perfect answer for a fluid way of going from CPU execution to GPU accelerated query processing. There's some shout out to Jana from TU Munich and their work. There's like emerging things where people start looking at basically sub operators, and maybe that's one, I don't really know, but maybe that's one answer that we can try and kind of pre-compile parts of query elements and then reassemble them in a way that allows us to compile for these accelerators. And then, of course, the other question is, how do we actually, once we have these accelerators, how do we share these across different queries, tenants? What about security? What about reliability? What about the OS operating system implications, and so on? So with this, I want to leave you with this thought and with one more thing. So I have very strong feelings about doing research in this space, and I think my feelings are similar to others, but I actually wrote a manifesto about this. So I invite you to actually go and read my manifesto. Joke aside, I think when it comes to specialized hardware research, often the mistake that we do is that we focus on performance. Basically, we say, what can I do to make this query go faster? And that, I'm not saying that that's not a challenging endeavor, but as research, perhaps it's a bit shallow. Because in the end, when it comes to just pure speed of things, the lessons I learned is that specialized hardware is nothing magical, right? In the end, it's just another way of performing computation. You could do it the same way by using a larger CPU or more CPUs, or spending $1 million on much more machines. So what I think that specialized hardware research in the context of databases or other kinds of data-intensive operations should look at is understanding what other properties we can improve by using these devices. So you can speed up your database, but then the question should be, when I do this, do I actually gain, for instance, significant energy improvements? So the database is faster, but did I save some money in the process? Or as you saw with the hybrid, with the in-storage processing, maybe it's not that the specialized hardware is faster in filtering things out than the CPU, but by removing a bottleneck in the right place, it basically enables the system to scale further, or to be more elastic, or to simply solve a problem it couldn't solve before. And I really want to invite you, again, this is half joking, but I want to invite you to think about not only performance, but other things that you can bring. I think some of you mentioned, security. I think that's, again, one of those spaces where, to me at least, it's a very exciting question of, can we maybe use specialized hardware not to offload something that the database is doing, but basically introduce new operations into the database, like privacy preserving computation, or self-auditing, or encryption of things in a way that doesn't actually slow down the data business, but gives you these nice features. So with that, I will stop and kind of open up for a very short round of questions. And then I'm happy to answer any more questions during the day. But I really wanted to kind of challenge you a little bit, or just bring this thought in, that we should not be thinking only about performance. You should always think of what other good things you can do with these ideas. And I think that's really the key for impactful research, is to bring kind of these benefits in different areas. Okay, so questions?